let me introduce our next speaker. So Chrysanthe Preza is coming from the University of Memphis. There's a little bit of overlap between your all's bio because she did her Doctor of Science at Worcester as well, Washington University, St. Louis. Chrysanthe is now, she's been at, I guess, University of Memphis since 2006, is that right? Almost 20 years?
Yes.
And she just told me before this she gets bonus points because she's been department chair for 8 years. And she's released from her duty in August, so congratulations on that.
Thank you.
Yeah. Too many awards to mention in this one, but you're also a fellow of the Optical Society of America and SPIE, and you'll be talking about efficient illumination, structured lighting for microscopy.
Great. Thank you very much for the kind introduction. Computational imaging for 3D fluorescence microscopy. And so in our work, we focus on developing imaging models to abstract the physical phenomena that take place to create an image. And then we use those as abstractions to develop algorithms to then process the data and get more suitable images for applications with higher resolution and contrast. And this approach enables us or allows us to come up with ideas to improve the way we collect the data and even make changes to the instrument for better efficient data collection and algorithm development. So over the years, we've worked on developing algorithms to improve restoration results by reducing artifacts produced by depth-induced spherical aberrations when you're imaging deeper into a fluorescent sample. And we did that by characterizing the points per functions variation with depth and then spatially, and we develop algorithms accordingly. Alternatively, we also, through wavefront encoding, we engineered the points per function to be less sensitive to these spherical aberrations, which then allowed us to use simpler computational methods to produce restorations with reduced artifacts. And today I'm going to talk about, instead of changing the detection path of the instrument, of the commercial microscope, changing the illumination path by introducing structural illumination, which then enable us to do OTF, or optical transfer function engineering, to create a more efficient and effective structural illumination microscopy with a tunable instrument. So I'll talk more about that. So a little bit of a background, because we have a diverse audience. We're talking about accomplishing 3D fluorescence microscopy by scanning a fluorescently labeled sample. Images are obtained by axially scanning the sample and getting a volume that, because of the properties of the instrument, this anisotropic points per function intensity, we know that 90% of the light in each one of the 2D images that we capture with the camera is indeed out of focus light. So this was very well known, and back in the early 80s, it was proposed to use digital processing, at the time 3D deconvolution, to produce a volume, a 3D volume that's a better representation of the sample. And then about 28 years later, we went beyond this 3D deconvolution. We proposed a method that used depth variant, multiple depth variant points per functions to get improved results. And then later, of course, we had spatially variant points per functions. Computational optical sectioning microscopy was what it was termed in the early 80s. However, wide field microscopy, 3D wide field microscopy is known for not having the optical sectioning capability. If we look at the Fourier transform of the points per function, we know that this limited bandwidth optical transfer function has a distinct missing cone of frequencies. And because of that, nothing can be transmitted through that cone, which leads to the lack of optical sectioning capability. And structural illumination microscopy overcomes this problem, and the paradigm is based on the fact that we can overcome the OTF's missing cone through frequency shifting. So imagine we have an object that only varies axially, like the one here, and so its Fourier spectrum is indeed just lies within the missing cone of the OTF, and so what you image is a uniform image, so you don't see the object. But if you're able to shift the object spectrum by some amount, by some frequency, then you can nicely position it within the bandpass of the OTF, and then you can indeed image part of the spectrum, and so you have an image that's a Bender representation of your object. So as we know, we can accomplish this phase shifting through modulating the object with structural illumination. So that's the basis. And in 2000, the late Mats Gustafsson showed that you can use a two-dimensional sinusoidal structure pattern to illuminate a sample by laterally phase shifting the illumination. You can get phase diverse images, which you really need to demodulate the information being captured. And then he proposed a set of computations to separate and shift the different components due to the sinusoidal pattern, and then you can extend and recombine these frequency components to get a new spectrum of the with extended frequencies, which gives you now up to an improved lateral resolution of up to a factor of 2. So that worked really nice, and that was the really the game-changing by using structural illumination since then. Now, I do want to point out that this is a multi-step approach to computing these improved images, but optimization methods that have been applied since then to structural illumination data can provide more robust results than this method, and I'll return to this point later. So this frequency shifting that I just described, essentially we can think about it as producing an effective structural illumination optical transfer function. And so we know that I showed you earlier, the optical transfer function for wide field microscopy, and because of this modulation with the sinusoidal pattern, in 2D SIM you get a replication, and so you get this extended effective optical transfer function in the direction of the illumination pattern. So if you want to create improved resolution in all directions, of course you have to rotate your pattern. And so later in 2008, Gustafsson showed that he could create a three-dimensional structural illumination pattern using three-wave interference, and so that improved the resolution both laterally and axially, and also provided 7 replications of the original OTF, so you got not only extension of the resolution, but also clearly filling in the missing cone, and so now you have an instrument that has a true optical sectioning capability. And of course, if you can do this in 3 directions, you can see that you get an OTF that's extended in isotropically. So I want to talk about a little bit about solving the SIM inverse imaging problem. I mentioned the original algorithm that was termed the generalized Wiener filter method, that has the multi-steps and it involves a filtering for deconvolution. So obviously it's non-iterative and it's fast, but it produces negative values, and it provides some regularization, but it's just like the Wiener filter, so it's not very robust. It does mitigate noise, but you do sacrifice the achieved resolution, which is what you're trying to get with structural illumination. So the optimization methods that have been developed over the years. They come in different flavors because they use different cost functions and priors. So one method is the Richardson-Lucy that maximizes the log likelihood. One method that we develop is based on the conjugate gradient descent method and minimizes the mean square error with positivity constraint. And of course, these methods are iterative, and there's also a concern about the convergence of the algorithm, so that could be an issue, but they do offer an ease in enforcing constraints, positivity, regularization, etc., which they can give additional benefits in getting more accurate results. So here's some results that we showed. This is in simulation, but we were really interested in investigating how well do you achieve resolution, both laterally and axially, and the arcs here show the theoretical sim limit and the intensity profiles at those arcs, and we showed that indeed with an iterative method, that like the model base with positivity constraint, you get improved results over the generalized winner filter. So one thing that I want to point out, and I don't want to dwell on equations here, is that the three-dimensional imaging structural illumination pattern is separable in two functions, one that is lateral and the other one that is axial. That was shown at the beginning by Mats Gustafsson. But in development of three-dimensional methods for three-dimensional processing, some people miss that part. You have to use the correct imaging 3D model, which is the one shown here, which basically the point that I want to make is that the lateral part of the modulation of the structure pattern modulates the object, while the axial part of the structure pattern modulates the points per function. You have to take care when you do the restorations that you have the correct model, otherwise you create artifacts. And okay, so this is some experimental results from an actin filament in U20 cells, and here again we're showing the same thing, that iterative methods provide better results than the generalized winner filter, and in fact the point here was the improved axial resolution. It's harder to argue maybe the fine structures in the 2D. This is like a blow up of that region, and so let me just show you the bottom row where you can see the cut through in the XZ space, and clearly you can see the improved axial resolution here and optical sectioning capability that is being retrieved with our method, the 3D model base with positivity constraint. So some newer, more recent approaches that we use is leveraging the plug and play methods, which I trust many in the audience are familiar with. Plug and play methods use image denoisers as image priors. They have the capability of integrating then physical and learned models of all the imaging models that we spend years developing for the image formation, and then we can benefit from using pre-trained denoisers like deep network-based Gaussian denoisers that are just trained to do simply the denoising, but you can integrate them with advanced optimization algorithms like the ADM algorithm to replace the proximal operator and improve your convergence of the algorithm and get results faster. So we have applied plug and play based on ADMM algorithm and DNCNM to structural illumination microscopy. We think this is the first time that this was used in SIM. And here I just show you some results that we reported recently at Photonics West. These are different sections that are being processed by a 2D plug and play method, and we're comparing the results that we obtained here in this column to the results that you can obtain with a full 3D processing with the generalized Wiener filter. So the point is that our 2D single slice processing method based on plug and play sim gives good results that are comparable to the ones that you can obtain with the 3D processing. So this is really promising, and we've used the SCICO library, the Scientific Computational Imaging Code, as a starting point, and then we had to adapt the given code there for SIM, where you have to do more fidelity splitting here because you have multiple images for, as I mentioned, because of the phase diversity. Okay, so over the years, there have been multiple structural illumination microscopy systems. The grid projection system that is incoherent and it uses 3-phase images. The 2D SIM that I showed you, the example 2-wave, also uses 3-phase images. The 3D SIM based on 3-wave uses 5-phase images, but it provides optical sectioning and super resolution, the first time that you could have that, versus the other previous systems were not capable of doing that. And a new system that we have been developing for several years now, which is the only 3D SIM incoherent light-based system that creates the structural illumination pattern using a prism, and I'll talk a little bit more about it. So compared to the 3-wave illumination system, it only needs 3-phase images, so you get 40% data reduction. It has decoupled lateral and axial modulation frequencies, so that gives you more degrees of freedom to design your illumination and engineer your optical transfer function. It offers tunable lateral modulation, and you can optimize it further by picking the shape of your source. So this is a collaborative project with the group in Valencia headed by Genaro Saavedra. So I want to acknowledge the co-authors here that did the heavy lifting of the work, but we have some of the earlier papers here that began the process. And I just want to show you here the basic principle that we started our first design with the biprism. Here is shown to be illuminated by a point source. So as you move, so the point source, the prism creates 2 virtual sources, which then they are interfering, and they produce the structure pattern. And so here, what you see in the animation, as the biprism is moved axially, you are impacting the modulation frequency of the pattern at the sample space. So this is using this principle, the first design of our system used a multi-slit array source, and so the pattern, the 3D pattern that we got it was modulated by an axial visibility function. So along the z-axis, you see these regions of confinement where you have high visibility of the structure pattern. So proof of concept results with the USA Air Force pattern that we tilted so we could get images at different depths, and if we zoom in this region, you can see the parts that were modulated, and those are the parts that are in focus, and you can retrieve that information, as you can see in these restoration images here. The zoom up here shows us that we get double the resolution almost. It's 1.8 because of the frequency we use, the modulation frequency, and we get improved results versus the only other incoherent base instrument, the apodome, which is the grid projection, in which you are forced to use low modulation frequencies. So here it was a slit array, so if you change the number of slits, then you can get a different OTF. and you can, if you change the distance between your slits, you can get a different OTF, so degrees of freedom where you can engineer your optical transfer function. So moving on, we improved our design by replacing the Fresnel biprism with the Wollaston prism. Has better optical properties. It works between 2 polars and a quarter wavelength plate. Again, axial displacement of the prism gives you tunability of your modulation frequency, and rotation of the second polar of the analyzer allows you to create the phase change in your structure pattern, so you don't have to move your prism. And proof of concept experimental data that shows that you can calibrate it once, you get a linear response of the structural illumination pattern phases with the rotation of the analyzer. So you can now, instead of a slit array, you can put an extended source, a quasi-monochromatic extended source, and the axial visibility here can be, it depends on the source. So again, you have regions where the structure pattern is very good visibility, and then as you move away axially, that pattern disappears. This is experimental data that we got from a mirror. So you see we verified the visibility function, and this is a way that it allows us to compute the visibility function from this mirror data, which we did, but also we showed that you can easily take an image of the source. In this case, experimentally, we used a slit, so it was like a square source, and if you take the projection of this source along perpendicular to the direction of your illumination, then you take the 1D Fourier transform based on the central theorem, you get your visibility function. So this is really nice because we can characterize the system quickly and easily. Yeah, thank you. So again, here you can engineer the optical transfer function by choosing the size of the source that you're using, the extended source, and by tuning the modulation frequency, so you can see the footprints of our OTFs. The dashed line is the outline of the 3-wave SIM, and so you can see that there are differences in that we can always maintain the 3D resolution in our instrument even when we reduce the lateral modulation frequency, which that can be important for some applications where you cannot have high modulation frequency if you have scattering and thick samples. So in conclusion, I talked about a tunable SIM approach that gives you 40% data reduction. You can engineer your optical transfer function, and you can determine the visibility easily by inspecting the source, and you can, by integrating new methods like plug and play, you can have more efficient SIM system. So I want to thank my collaborators and the developers of the Psycho Library, our funding, and your attention. Thank you very much.
I think for sake of time, we'll just move on to the coffee break, but the speakers will be outside at the coffee break. You can meet up with them. So I would like to thank all the speakers again.
Next session is in 11:15.